Another term for it, we take the what? Kind of logarithm. Okay, so let's talk briefly about logs. You don't have to write this. You can write this on a piece of scrap paper if you want. What are logarithms? What's that mean? This is how we deal with really big and really small numbers, right? Again, you don't have to write this, but you can. It's kind of like, what's another way we deal with really big and really small numbers? Yeah, but this one goes a step further. In scientific notation, we at least get rid of like all those extra numbers, but the number itself is still really big and really small, right? In other words, writing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 1, we could write this as 1 times 10 to the negative 13, right? And that is certainly cleaner, right? But it's still actually the same number. It's just written in a way that's easier to work with. Logarithms say, so this is the number. What if we took that number and actually made it into a smaller number? What if all we dealt with was we just said, this number is that? Does that make sense? What if we didn't worry about this? What if we just said negative 13, right? Now, we've taken a big number and or in this case, a really small number, and we've actually just turned it into a 2-digit number, right? So a logarithm is what exponent do you have to put on some base? So the log base b of some number a is what exponent you would have to put on the base b to get a, okay? So if we want to know what the log of some number is, what it is we say, okay, what exponent would I have to put on this number here to give me that number? What exponent here gives me that? And if we don't write this here, our default is 10. And you know why our default is 10? Because we count in tens. So if they just write log, then we're talking about 10. But you can take the log of 2, in which case we're saying what exponent of 2. So we are going to work in log base 10 in chemistry right until we don't. But right now we're going to work in log base 10. And so what we say is this. The log of 1 times 10 to the of 1.0 times 10 to the negative 13 is negative 13, because what that means is if we do 10, the base, to the exponent negative 13, it equals 1 times 10 to the negative 13. Does that make sense? And that works really nicely for clean numbers, right? So you can imagine that the log of 1 is just 0. The log of 10 is just 1, right? 10 to the exponent 1 is 10. The log of 100 is 2, because 10 to the exponent 2 is 100. The log of 1,000 is 3. So do you see how you can make a graph that grows very slowly out of numbers that grow very quickly? And again, why is this useful? This is useful because let's go into Desmos and let's talk about dealing with acids and bases. Ready? Okay. So if I wanted to make a graph of, thank you. Oh, where's my browser? There's my browser. The reason we use logs is just because otherwise it becomes very hard to represent numbers. Okay, that's just not loading, so whatever, we're going to do away with it. But in other words, if I had a bunch of acid concentrations and the concentrations of those acids, so here's solution A, and the concentration there is 1.0 times 10 to the negative 6 molar. And I have B, and it's 2.3 times 10 to the negative 6 molar. And then I have C, and it's 4.9 times 10 to the negative 6 molar. But then I have D, and it's actually 3.5 times 10 to the negative 3 molar. And then I have E, and it's 1.8 times 10 to the negative 1 molar. Are these all concentrations we could actually work with? Any reason we couldn't prepare any of those? Right? Sure, you do a dilution, you weigh out the mass. We can make all those solutions, right? So now if we graphed these, and then maybe we did how long it takes to react, right? Like time to react, who cares, whatever it is. Point being, it doesn't even matter what the time value is, because the x values of these, if these are the concentrations, right? These are also tiny. If this one here is times 10 to the negative 1, then all the rest of these are going to live here, just in a tiny dot altogether. Does that make sense? Because this would be, if this is 3 times 10 to the negative 1, this would be 2 times 10 to the negative 1. This would be 1 times 10 to the negative 1, right? And all of these are times 10 to the negative 5 and 6. They just live there. Does that make sense? They are all scrunched up together. And so the graph becomes useless. Does that make sense? But if we take the logs, of each of these, well now, so if that's the concentration, now let's take the log of the concentration. So on your calculator, go ahead and do that. This is going to be exactly negative 6 because 1 makes it easy. This is going to be smaller than negative 6. It's going to be negative 5 point something. And this is also going to be negative 5 point something. And this is going to be negative 2 point something. And this is going to be negative 0 point something. But I don't know the answer. That's going to be negative 5 point, oh God, I don't know. Like fairly low, 5.1, 5.2. Somebody help me out? What's the log of 2.3 times 10 to the negative 6? By the way, on our calculator, how do we do scientific notation? 2.3 e negative 6. And how do you get that e on these calculators? Second function, and then what? I think it's the comma button. Is that true? On the yellow calculators? Can somebody check that? Is that how we get scientific notation? Second function, comma? Right? And that gives us the e, and that it might even show it as double e, but that's scientific notation. So take the log of that. What do we get? 5.63. Cool.
It'd be 6.4.
Whatever. Okay, that's fine. 5.64. What about this one? Take the log of 4.9 times 10 to the exponent negative 6, right? Do that on your calculator. 5.31. Okay. And then this one, this is going to be negative 2. Oh God, probably high, like 2.6, 2.7, 2.60. Great. And this one's going to be, this is going to be, oh God, I don't know. This is going to be 0.9-ish, 0.8-ish. What is it? 7.4? Okay, cool. All right. So again, could you put these on a graph and have it be neatly? Right? So when we have really big and really small numbers and we want to compare them, it really helps to take the log because we compress those numbers into a smaller range. Does that make sense? That's all. It's just a math trick. It's a math trick to take numbers that are really far apart and compress them. Where log isn't very useful is where numbers are really close together, right? Where we wouldn't use it, try this. If we had 2.35 times 10 to the negative 5, and we had 2.64 times 10 to the negative 5. Those are really different numbers. And yet if you take the log of both of them, try it right now, you'll find that here, log is actually unhelpful. It's going to make these look really close together. Try it. See what you get. Try it out. No questions right now. Take the log of this. Unless it's how to take the log of it. Slide over. I will show you. Your problem isn't that you don't know how to do logs. Your problem is you don't know how to use scientific notation on your calculator. That's an important skill.
Is there a log button?
Yeah, it says log.
Oh, I'm blind.
That's fine. It's right there. And then, so I lied. The problem was scientific, was log. And then that gives us scientific notation, right? And we said what? Negative 5? There you go. So that one is negative 4.63.
Sorry, I didn't know.
No, you're good. Don't be sorry. So this one's negative 4.63. What's this one work out to? Negative 4.57? Yeah, so do you see how that compresses these and makes them look very close? So when we have numbers that are really close to each other, we tend not to take the log of them. That's not helpful. But when we have numbers that span a big range, a really big range, from really small to really big, it's helpful to take the log. So it's just up to you. Sometimes in math we do, sometimes we don't. For example, during COVID, when everyone would say like, well, what's the big deal? We had 100 deaths and last week we only had like 22 deaths, like worldwide. That's not a lot. The clever amongst us, and by clever, I don't even mean clever, just those who like understand like exponential growth said, well, put that on a log chart and you'll see that the log growth of that is linear, which means that these numbers are growing linear, but that's the exponent on 10 that's growing linearly. That's a problem, right? That's how 10 deaths becomes 100 deaths, becomes 1,000 deaths, becomes 10,000, becomes 100,000, becomes 1,000,000, becomes 10 million. That's unsustainable, right? Does that make sense? So logs let us deal with big spans of numbers. So when we calculate the pH, it's important to remember that the pH is just the log of the concentration of H+. But because the concentration of H+ is almost never above 0, or above 1, this one here. Because it's almost never above 0 point something, right? This will almost always give us a negative number. And if we're constantly dealing with pH, does it make sense to always be working with a negative number? No. So we arbitrarily say that when we take the power of something, we take the log of that number and we flip the sign. So we don't take the log of H plus, we take the log of H plus, and then whatever that sign is, we flip it. And that's the definition of pH. It's the negative log of the concentration of H plus in a solution. That's how we calculate pH. And that's why smaller actually means bigger, because what smaller actually means, a pH of 1 actually means you have 1.0 times 10 to the negative 1 molar HCl. Does that, for example, does that make sense? Whereas a pH of 2 would be 1.0 times 10 to the negative 2 molar HCl. How much stronger is this one than that one? When we go from pH 2 to pH 1, how much more acidic is it? It's 10 times. Every time you take a step on the pH scale, you're multiplying by 10. So like comparing pH 1 to pH 6, it's not 5 times stronger. It is 10 to the exponent 5 times stronger, which is 10,000, right? So when something is pH 1 versus pH 6, it is 10,000 times stronger. This is why vinegar can be pH like 3 and it's not dangerous to you, but then, or it's even like 2.5, but then like something that's pH 1 is dangerous to you. It's because it's not 2.5 times stronger. It's 10 to the exponent 2.5 times stronger, which is a lot stronger. So if you want to know the pH, you take the negative log of the concentration of H+. So now let's do this for this particular acid. The nice thing about a strong acid, nitric, what would nitric acid be? Nitric. As soon as we see ic, we know that what kind of acid is this? It's a binary acid. Is this like HN and we'd need 3 N's because do those end with ic? They end with ic, but what do they start with? Hydro, so that's not it. It ain't that. Nitric, what's the, we have H obviously, and what's the nit part? It's nitrogen. Nope, not nitrogen, nitrate. What's the nitrate ion? NO3, does anyone remember the charge on nitrate? That's 1, good, very good. What are the ones that are 2? Carbonate's -2. Sulfate's -2. Sulfate's interesting because most of these are NO3, CO3, ClO3. Sulfate is SO4 and it has a charge of -2. What's phosphate? PO. And its charge? -3. Anyway, this is nitric acid. So if we have the NO3 ion, which has a charge of -1, we have hydrogen that has a charge of +1. Obviously, how many of each of these do we need? 1 hydrogen gives up an electron, 1 nitrate takes an electron. So we get a formula of HNO3. Okay. HNO3 is a strong acid. So HNO3 dissolves in water to form H+ ions and the NO3 ion, and this is not an equilibrium. All right, strong acids don't form equilibria. Strong acids, what do we call splitting apart? Yeah, very good. They dissociate completely. All right, so strong acids dissociate completely. All right, the other way you could write this, by the way, if you felt like it, you probably haven't seen this before. There's another way to say this. We could say that HNO3 reacts with water and it forms the nitrate ion, because actually when you release an H+ ion, it doesn't float around freely. It actually finds water and forms what? That. You'll see this. These actually mean the same thing. In other words, H+ ions, when they float around, are going to be attracted to the polar side of water. Which side of water is the H+ going to be attracted to? Is it going to hang out over here, or is it going to hang out up here? Why up there? What do we call this? dipole. This side is slightly, great. Why is this side slightly negative? Oxygen is more electronegative. Good. We would have a dipole here and a dipole there. The left and right of it would cancel. It would give us the big one. Good. So you'll see sometimes these used interchangeably. You'll see hydrogen written as H+. That's fine. You'll also see it written as H3O+. Those are actually the same thing. It's just the reality is that when an H+ gets released, it finds itself a water and it hangs out with it. Does that make sense? So you can use those interchangeably. Yes, ma'am? Nope. We would now call this the hydronium ion. The hydronium ion. Like hydrangea. Hydrangea, hydronium. If this spilled over the page for you and you wrote it on the desk, you probably just want to highlight it and slide it over. Maybe shrink it down a bit, just like that. Okay, because obviously that'd be silly. So now let's look at this reaction. And what do we have? Well, we need to figure out the concentration of H3O+ or concentration of H+. Either, doesn't matter, it's the same thing. Well, what do we know we have? We know we have 25.0 milliliters of acid, right? Okay. Do we all work in milliliters? So what should I do? Yeah, so where do I want to put milliliters? We're figuring out how much H+ we have. It's called hydronium. So what do I want to do? I want to not talk about mils. Where do I put it? And obviously, what are we going to work in? Okay, do we have numbers for this? 1 and? Great, did I put those in the right place? I think so. Great. Okay, if we stopped calculating now, what would we know? How many liters of acid we have? My pet peeve is when I ask that question, people just say a unit. It's like, okay, good, but like what's context? What's that mean? That sounded more negative than I meant it. I just meant, I should have said it in a positive sense. What I would encourage you to do when you answer that is not just say the unit, but say like the context for it. See, that was negative. Oh, see, I don't mean to be negative. I'm just built that way. Some people are tall, some people are short, some people are cripplingly negative. Anyway, so now the purpose of this is we want to know how many moles of H+ we have, right? So, actually, we are wasting our time completely. The concentration is just given to us, isn't it? Why am I doing this? It's in my cheat sheet. The cheat sheet does not show any of this. Okay, let's figure out how many moles of H+ we have. You know what we're going to do? We're going to just go ahead and divide by this number anyway. Yeah, no, that's silly. Let's not do this. Just erase that. This is silly. What's the concentration of... I did need to do this, but what I needed to do was actually much easier. We know that we have what? We know that we have 1.40 moles of HNO3 in every liter, right? That 25 mils, that's a complete red herring. Doesn't matter for concentration. And HNO3 turns completely into H3O or H+. Doesn't matter which one you go. So for every 1 mole of HNO3, we get 1 mole of H+. Does that make sense? Now, you will probably never show this step again because this is just obvious. But do we see that? It's actually worth showing at least once in a while to show when we get the concentration of H+, it's not really this. This isn't what makes this an acid. This is what makes it an acid. Does that make sense? So it's not the fact that we had 1.4 moles of this in every liter that really makes this acidic. It's the fact that all of that turned into this. Now, because it all turned into it, is the number going to change? No, right? We're multiplying by 1 and dividing by 1. So the answer is we end up with 1.40 moles of H+ in every liter. Does that make sense? And we could just call that 1.40 molar H+. All right, does that make sense? But what I want to stress is we have to think about the H+, not the HNO3. Because HNO3, if it didn't dissociate, it wouldn't be an acid. It's the fact that it releases the H+ that makes it an acid. Is that comfortable? And then calculating the pH is trivial. What does pH equal? The negative log of the concentration of H+ or H3O+. I'm going to write it as H3O+ here, just to show that it's the same thing. And that means we're taking the negative log of what? 1.40. We're going to get a negative pH here, which is allowed, by the way. What's the negative log of 1.40? What do we get? Negative 0.146. You can have a negative pH. That's okay. A negative pH is allowed. It just means that our concentration has gone above 1. 1 is a pH of 0. Anything bigger than that is going to be negative. Yeah. Does not matter. It's a red herring. Doesn't have anything to do with it. It might be important later on, but it has nothing to do with this math, because does concentration depend on how much of the stuff you have? No. Now, if we diluted it, it would change. Yeah. Okay. So pH, easy to calculate. But now, most acids are not strong acids. Most acids exist in equilibria. And that means that for most acids, we have something here, HA, and when it reacts with water, what we end up with is what? Well, the A ends up by itself, right? And what charge will it now have? Minus, because what does the H leave with? Does it take its electron with it? No. So it leaves as an H+. It's going to find a water, and we're going to write that as H3O+. Does that make sense? Okay. So now we could write a KEQ statement for this. But because we're talking about an acid, we're going to call it KA. Doesn't mean anything. It just helps us remember that we're talking about an acid. Does that make sense? What would the Ka statement for this acid be? So concentration of H3O plus times the concentration of A minus. And then on the bottom, we'd have the concentration of HA, and we'd have the concentration of H2O. Now, there's one thing that should jump out at you here as being kind of weird to calculate, which is what? What is weird up here that's going to jump out at you and be like, really?
The concentration of water?
Yeah. Now, for the record, you can actually calculate the concentration of water. Because if you have a liter of solution, and the only thing in it is water, you have a liter, it's water, and if you know the temperature, could you figure out how many moles that is? Sure. And so then, could you just divide how many moles of water you have by the fact that's a liter? Yeah, you can do that. And we know that actually a liter of water weighs a kilogram. So we could say 1,000 grams of water in 1.00 liters, right? And we just have to convert grams to moles, right? We could put grams of water on the bottom and instead put moles of water up here, right? How much does a mole of water weigh? Well, 16.00 plus 1.01 twice, so 18.02, right? Somebody do that on the calculator? What do we get? 1,000 divided by 18. It's going to be, it's roughly 1,000 divided by 20, so it's going to be 50, but bigger. So how much? 55.5. Okay. Yeah, so this is roughly the concentration of room temperature water, right? Because room temperature water weighs 1,000. But here's the thing. You could include that in this calculation. No reason you couldn't. But even though this reaction actually uses up some water, how much of the water typically do we use in an acid? Even in a really concentrated solution, we have a ton of water and just a little bit acid or base, right, relative to it, right? Like even when we made really concentrated NaOH solutions, that might be 40 grams of NaOH in a whole liter of water. Does that make sense? So 40 grams out of 1,000 grams. In other words, in 2 sig fig land and 3 sig fig land, this number basically doesn't change. Does that make sense? And so we actually go ahead and assume that the concentration of water is basically constant. Even though it does change, it changes way on the margins. Does that make sense? So we can assume that the concentration of water is constant. In fact, that's what Ka means. Therefore, the concentration of H2O gets folded into the K value. We just put it over here with K, and now we call it Ka. So it's not really called Ka until we move the concentration of H2O over, and just treat it as a constant. Does that make sense? If you were doing hyper accurate calculations with very strong acids, then you would actually have to go back and work with a KEQ value, and you'd have to deal with the concentration of water. For all practical chemistry, it doesn't matter. Does that make sense? So we are making an assumption here. In math, we make an assumption. And by the way, that means that none of the math we're about to do is totally true, but it's true enough. This is a lot like parenting or teaching or friendships or marriage. Nothing's absolutely true, but it's true enough. You know what I mean? How was dinner? Dinner was great. Britt, how's my hair look? Your hair looks good. It doesn't look good. She knows it doesn't look good. I know it doesn't look good. It doesn't matter. You say it. You know what I mean? Know what I mean? Hey, I've been writing this song. Do you want to hear it? Yeah. No, she doesn't. Of course she doesn't. Oh my God, she doesn't. But you say yes, right? Because it's true enough. The real truth you're expressing is I care about you and your happiness matters to me. Here, is it true that the concentration of water doesn't change? No, it does change. Is it true that it changes so little that we cannot worry about it for most practical purposes? Yes. And so in science, we do that a lot, where we can make an assumption, and as long as we work within strict parameters, that assumption's reasonable. We're going to do that a few times in this lesson to make our math easier. But if you wanted to be a real purist, I had a student a few years ago who insisted on doing all of these, including that number. I think he's a sociopath, but whatever. The point is you can do it. You want to be a sociopath? Go nuts. But what we usually then say is this. The definition of any acid's equilibrium state is that at equilibrium, the concentration of H3O plus at equilibrium times the concentration of the A minus, the stuff that's left over that used to be the acid but has given away its H plus, divided by the concentration of the original acid, again, all at equilibrium, will be constant. And we call that its acid constant, or its Ka value. You have to watch out. Some acids are what we call polyprotic. What's poly mean? Multiple, more than one. Polygon has many gons. Polyamorous has many amoruses, which I guess means like loves, because amour is love in French. The French have the word love and like, and they mean the same thing. Amour, it means like and love. See, in English, we have different words for those things. We like something and we love something. The French, they just have one word. They have to use both. Yeah, that's different. Adore isn't the same thing as love or like. It's its whole own thing. We also have adore. But we got nothing on the Greeks. The Greeks had 4 different words for love. They had like koine love. They had agape love. That's like brotherly love. They had eros. That's like romantic love. And there's another one. I can't remember it, but it's there too. Anyway. Polyprotic acids, they have poly, many, protics. What's a protic? Well, ick makes it an adjective, so polyprot. What's a prot? It has many prots. What's a prot? Proton. What's another way of saying a proton? Well, proton is a hydrogen without an electron, right? In other words, it's an H+. So a polyprotic acid has more than one H+. What's an example of an acid that has more than one H+? Yeah, if we look at sulfuric acid, this actually isn't one acid, it's 2 acids. And we actually have to treat it like that. The first one reacts with water, and this one, sulfuric acid, the first one actually goes to completion. H2SO4 is a strong acid, and it would give us HSO4 with a -1 charge and H3O+. This is a strong acid, so it's no equilibrium. All right? And that just means Ka is enormous. Ka is really big, such that we get a lot of this, and we have basically none of the H2SO4 left over. Does that make sense? So much so that we don't even bother writing it as an equilibrium. We just say it goes. But then the second one, HSO4, it can actually lose another electron, and it can give us SO4 with 2- and another H3O+, but this one has its own Ka value. Does that make sense? I don't know what it is, but it has its own Ka value. So each electron that it loses is actually its own equation with its own Ka value. Does that make sense? It doesn't lose all of them at once. It's easy to lose the first electron, or the first hydrogen rather. The second hydrogen is harder to lose. Can anyone think of one that has 3 hydrogens? H3SO4 doesn't exist, but H3 PO4 exists. And so that can become H2PO4 minus and an H plus. That 4 should be at the bottom. And that would have its own Ka value. And phosphoric acid isn't a strong acid, so that's an equilibrium. So that would have what we call Ka1, and it would have some number. And then now it can lose a second electron, and it would be H2PO4 minus can lose another electron, giving HPO4 2 minus. And that would lose an electron, and that would have its own Ka value. Boy, this new pen, I need to calibrate it. And we would have HPO4, and it could lose its own electron and give us PO4 3 minus and another H plus. I really need to calibrate this thing. It's killing me here. And that would give us Ka3, and each of those has to be treated as its own thing. Does that make sense? Each one is its own acid. So phosphoric acid isn't actually one acid. It's 3 different acids. It's H3PO4, and then it's also H2PO4 minus and HPO4 2 minus, and each of these behaves its own way. You'd have to write an equilibrium equation for each. As you can imagine, if you deal with this, you have a lot of equations to keep track of. Polyprotic acids get messy. We're not going to deal with them in this course, but if you take university chem, you will. Yeah?
Is the A in Ka a lowercase or a capital?
It depends on how I'm feeling at that particular moment. By convention, it's usually an uppercase A, but you're going to see me do both. Correct me if you remember. If not, it's not a big deal. Or is it normally lowercase? Now I'm having a moment. What did I put in the title? Well, you know what? When we look at the chart on the next page, it's normally lowercase. See, because there it is. Normally lowercase. But again, you'll see both. Okay, the nice thing is you can look these up. By the way, the bigger the Ka value, the more product you get. And in this case, the product is H3O plus, and that's the thing that actually makes an acid, right? So a bigger Ka value means that the acid is more acidic, pound for pound. Does that make sense? So looking here on this table, what's the most acidic acid? Chlorous acid. Chlorous acid, fairly strong, all right? Now, if you do the math, you're going to see it's still not that strong. It's not remotely as strong as the kind of acid that goes to completion. What's the weakest acid on here? Should jump out at you. This is one acid, and it's not very effective at all. It barely acts as an acid at all. Water. Water is an acid. Water will dissolve in water and every once in a while and give up one of its H pluses. But then, if you think about that for a moment, you're going to see that, well, it's an acid, it's also something else at the exact same time. Anyway, we'll come back to that. We'll get there. Put your hand down. Okay, let's get to work. So now let's take a look. Let's talk formic acid. By the way, formic acid has a better name. This is its original name, formic acid, but here's its structure. What would we call formic acid? You know what it's properly called. Methanoic acid. Very good. That was quick. Methanoic acid. What's the hybridization state of this oxygen? Hybridization state of this oxygen? SP what? 2? How do we know it's SP2? I agree. I like it. Yeah, it's got one double bond, which means it has one sigma. Well, it doesn't have one sigma. Yeah, this has one sigma and one pi. How many lone pairs did this have, even though I didn't draw them? 2 lone pairs. Good. What's the hybridization state of this carbon? I heard SP, I heard SP3, I heard Abdullah, I think say SP2. How do we know? Yeah, it still only has, how many lone pairs does it have that I didn't draw? None. Good. Is this flat or 3-dimensional? Flat, it's trigonal planar. How do we know that? SP2, 2-dimensional, right? What's this bond angle? I didn't draw it accurately at all. 120, good. Could we draw an energy level diagram for that? Sure we could. If this reacted with another methanoic acid, what would it form? Oh, sorry, if it reacted with methanol. If I reacted this with methanol, what would we get? Methyl methanoate. What kind of compound is that? It's an ester. Might smell like something. Cool, you guys are good. Okay, so we're going to use formic acid, HCOOH. This silly construction here tells us that's an acid, right? Even though it's a clumsy way to write that, we can picture that as being that double bond to O, bond to OH. So it's a convention that we do this silly OOH thing, which is silly, but it tells us we're dealing with an organic acid. Organic acids are never strong acids. Most of the time, they don't give up that hydrogen, just sometimes. All right? Which means that we have HCOOH, and it's going to react with water. And what is it going to form as products? Sometimes? H3O plus. 3 is not an exponent, so I'm not going to write it up there. And what else? HCOO negative. Good. Okay, good. Now, when we go to write a Ka statement for this, lowercase a, as I will recall, what will our Ka statement be? What goes on the top? Concentration of H3O plus and HCOO, that conjugate base, which we'll talk about in a minute, what that means. What goes on the bottom? Do we put the H2O on the bottom?
No.
Yeah, it's folded into Ka. You could put it there, but then you'd just call this KEQ, and you'd have to look up a different value. Ka has that water concentration built into it. All right? So we don't have to worry about it. Now, that there is the Ka statement, and you can go look this up. Every acid at normal room temperature has a known Ka value. I gave you a little table here, but every acid imaginable, and they also have those at every temperature imaginable. So what's the Ka value of formic acid here? Yeah, so 1.8 times 10 to the negative 4. If you wanted to write that as a decimal, you could say 0.00018. This is one of those ones where it's kind of on the verge of being simpler, but I still like the scientific notation because you don't accidentally add a 0 or lose a 0. There we go. Okay. Now, the question is, if we start with a 0.025 mole per liter solution, what's its pH going to be? Well, if we want to know its pH, what do we really want to know? pH is just what? pH is the negative log of H plus, or if we want to write it as H3O plus, that's the same thing. So what do I need to know? I need to know the concentration of H3O plus, but it asks at equilibrium. And of course, keep in mind, these are all at equilibrium. But is this value at equilibrium? No, this is what we start with. All right? So we are starting with some HCOOH. And how much of it are we starting with? 0.025 molar, right? What are we forming? H3O plus and HCOO minus. Now, for now, we're going to assume we start with no H3O plus. That's not true, but it's true enough. It's true enough. Britt, do you want to take a look at this lesson? Does this seem like it makes sense? It looks like a good lesson, Joe. It doesn't look like a good lesson, and she doesn't care. She doesn't want to take a look at it. But she says yes, and she says it's good because it's true enough. Because what she's really communicating is she cares. Is it true that water by default has no H plus ions in it? Or we're going to learn later that's not true. But it's close to true. Why? Why are we testing the paging system? Good Lord. No, we could test all kinds of things. We could test the turning out the power system right now. We could test the lighting the cafeteria on fire system, but we're not because it's the middle of a class. Honestly. We done? You watch. I'm going to start talking and it's not going to be done. I'm going to start paging again. I'm going to be grumpy. Okay, so listen. For the time being, we assume that we start off with no H3O plus and we start off with none of the, in other words, we start off with no products. This looks like every other equilibrium we've done. And so as every other equilibrium we've done, we know what to do here. It's even nicer because acids tend to have no coefficients here. They tend to be one-to-one stoichiometry. In fact, they are all one-to-one stoichiometry because we deal with the hydrogens one at a time. So you're never going to have an exponent. That's nice, right? So what can we put here? yeah, this is going to get used up, and it's going to get used up by some amount. And as it gets used up, what's going to be true here? And here? Awesome. So which means at equilibrium, what will the concentrations be? This will be? Very good. And this will be? And this will be X, and this will be X. Does that make sense? That's not so bad. And now can we put those values into our Ka equation? I can't see why not. We have the technology, so let's do it. This is going to equal 1.8 times 10 to the negative 4. And I'm going to slide this over. Hopefully I still have room for it there. All right, my fraction. What did we say on the top? What are these concentrations at equilibrium? X and X. And on the bottom? Okay. And what do we have here? We have a quadratic. Who earns? All right. This is 1.8 times 10 to the negative 4 still, obviously. This up here, what's X times X? X squared. And this is still 0.025 minus X. What should we do next? Multiply it over. Okay. So this will still be X squared. This will be 1.8 times 10 to the negative 4 times 0.025 minus X. Oh boy. All right. Kind of miserable, right? I'm going to move the X squared over. I'm going to say negative X squared. Okay. And then what's this? Plus 4.5 times 10 to the negative 6. And then obviously what's this? Minus 1.8 times 10 to the negative 4x. And what would be over here now? I've moved that x squared over. Why did I do that? What do we want this to equal? 0. All right. And I don't love my order here, so maybe I rewrite it just so I don't screw it up. Negative x squared. And can I tell you something else? I hate leading with a negative number. So do you know that, can we divide all this by negative 1? Any reason we couldn't do that? And divide this side by negative 1? Sure, of course you can. What's 0 divided by negative 1? 0. Cool. And what's negative x squared divided by negative 1? X squared. What's 4.5 times 10 to the negative 6 divided by negative 1? Yeah, minus 4.5 times 10 to the negative 6. And I'm going to put it at the end because it has no x. And what's negative 1.8 times 10 to the negative 4x divided by negative 1? Positive 1.8 times 10 to the negative 4. Yeah, the nice thing, when things equal 0, you can play a lot of math tricks, right? You can multiply by anything you want, divide by anything you want, and you're cool. Did I lose the x? I lost the x. All right, we're going to do a quadratic here. What's A? What's B? Yeah, and what's C? All right, everyone do it. I'm going to do it. You do it. Let's solve this. Right? X equals negative B. Okay, negative 1.8 times 10 to the negative 4 plus or minus the square root of 1.8 times 10 to the negative 4 squared. Hey, are these the numbers super ugly? Yeah, they are. Are we cool with that? Yes, you're tough. You're tough. All right, we're not cowards. We're not a bunch of physics students here. We're not afraid of numbers. We're chemistry students. We overcome numbers. We're not biology students. I mean, some of us are. But minus 4 times 1 times negative 4.5 times 10 to the negative 6 all over 2 times 1. Okay. And again, we're big boys and big girls. How do we do this in our calculator? One shot. All right. What do I have to put the top in? A bracket. Negative 1.8 times 10 to the negative 4 plus the square root of, what do I need here after? Another bracket for all that. 1.8, and I should put this in a bracket. 1.8 times 10 to the negative 4, and I got to square that, right? Minus 4 times 1 times negative 4.5 times 10 to the negative 6. That's just for the negative number. That's for the square root. That's for the top, right? I think. Looks good. Divide by. Now I need a bracket for the bottom. 2 times 1. Close the bracket for the bottom. That should be good if I haven't screwed up. Maybe I screwed up. We'll find out. See if we get the same answer. I get 0.00203. Cool. And then, of course, what do I have to do with this? I also have to try. Yeah, the only difference is instead of being plus the square root of all that jazz, it's minus the square root of all that jazz. And I get 0.022. Okay. We get two answers there. Oh, and it's negative. Okay, well, that's problematic. So which one of these answers? So x either equals positive 0.002 or negative 0.002. Which one of those is going to make sense? Yeah, why can't the negative one make sense? Because our change can't be negative. Because if our change is negative, then the concentration of this would have to go up. And can it? No, because we don't have anything to make it. So this answer is absurd, right? It fails that classical informal fallacy of reductio ad absurdum, right? It is an absurd outcome, right? So this has to be the accepted value, right? So we would say x equals 0.00, what did we get? 203? And I'm in 2 sig fig land, right? So that would be 20. Does that make sense? Could I keep an extra digit now if I felt like it? Sure. But because we're adding and subtracting, it's not actually going to make a difference, right? Does that make sense? Okay. So what are my equilibrium concentrations then? Well, this is actually easy. What's this equilibrium concentration? 0.0020. What's this one? 0.0020. And what's this one? 0, and then we took, this would still be 2, right? And then we took 2 away from this, right? So that'd be 3, right? And then by sig fig rules for adding and subtracting decimals, that's going to have to be where we stop because that's where the number above stopped, right? Oh, good. Testing the buzzing system. Testing the loud 60 hertz hum. Do you know why that's 60 hertz? No. Do you know why it's 60 hertz? Do you know where that hum comes from? That hum is everywhere, all around you, all the time. That's actually a multiple of 60, which is a different discussion, but that's probably, if I had to guess, I'd say probably maybe 480. But still, 60 cycle hum comes because, how's our electricity made? By a spinning turbine down at the falls. How fast does that turbine spin exactly? 6 times every second, which means our power goes up and down 6 times every second, which means it releases radio frequency waves at 60 cycles every second, which means any unshielded wires you have, pick that up and include it. So if you have a wire that's badly shielded somewhere in your system and you connect it to a speaker, you pick up some of that electromagnetic radiation from our power lines. That's why, if you have a guitar with pickups and you put near power lines, you'll hear that same hum. Though, again, that's being multiplied by something, which is interesting. Anyway, doesn't matter. 60 cycle hum. All right, now, we've done all the math, and the danger in this is we do a bunch of math and we forget what the question was. But what was the question? The pH. And what did we need to get the pH? The concentration of H3O+, the hydronium ion. Good. Do we know that now? Can we answer our question now? Yeah, what do we have to take? We need to take the negative log of the concentration of H3O+, and we know that that means that the pH is the negative log of the concentration of H3O+, which at equilibrium, which we know to be 0.0020 molar. And that, if that was a 1, this would be 10 to the negative 1, 2, 3, right? So this would be negative 3. It's double that. So this should be negative 2.8-ish. Oh, and not negative because we took the negative. 2 point what?
698.
Great. And how many sig figs are we working with here?
2.
So it's 2.7. Good. Okay. A lot of math there, yeah? How was that? Does it feel okay? Yeah. No, pH does not have a unit associated with it. It's an index. It's just a number. Yeah. Yep. Sorry, guys. I'm so sorry. I can't hear. Could we shut up? Yeah. You will get cases potentially where both values are actually valid, but you still have to think once it hits equilibrium, it stops, right? So then the question would be, which of these values will it get to first? And you'd have to go look at your question, and it'll be the smaller one, right? Because you're talking about drop. So the answer is once it got to that first smaller drop, it would be in equilibrium, and there'd be no reason for it to move. So if you get two values that are both valid, the one that is smaller, the one that it causes the least change, will be the one that happens first, and that will result in a stable equilibrium. That doesn't come up too often. Usually one of them is just straight up ridiculous, but there are cases where both values are valid, and then it would be the smaller change, typically, unless there was some external force that made there some reason why the second one would come up. Did that answer your question at all? Wow. Miracle. So the pH of, and what was our actual question here? It was 0.025 molar formic acid. So the pH of 0.025 molar formic acid is 2.7. By the way, if this had been not formic acid, if it had been a strong acid, how much stronger would it be? What's the negative log of 0.025? Can somebody do that quick?
0.025.
Yeah, what's the negative log of 0.025? 1.6. Which is over 10 times stronger. So if instead of formic acid you used a strong acid like HCl or something, it'd be 10 times stronger. And formic acid, as weak acids go, if you look here, is one of the strong-ish ones, right? Where's formic? -4, right? It's not like a super weak acid, and it's still over 10 times weaker than a strong equivalent. Yeah.
So with our like Aster lab, we use like I don't know the molar of the H2SO4. What would the pH of that be?
Well, H2SO4 is a strong acid. It's first hydronium. So you could just take the concentration of the H2SO4 and just take the negative log of it. And the second hydrogen, if you look up the Ka value of the second hydrogen on H2SO4, it doesn't do much. It'll modify the pH at like the third or fourth decimal place, but not where you meaningfully care about it. Did that answer your question?
Yes. What was the concentration of that one?
The sulfuric acid we used was strong. We used like 3 or 4 molar. It was a concentrated strong acid. It was nasty stuff, yeah.
What do you think the negative log of 0.025 was?
Oh, I was just saying if this had been a strong acid that dissociated completely, but of course it isn't. And so if you look here, that's like less than 10% as acidic, right? Like instead of 0.025, we only actually get 0.002 moles of H3O plus, and that's because this Ka value is negative. And it's small. It's got a negative exponent, which means that we are mostly keeping our reactant. We're only making a bit of product. Does that make sense? And most acids work that way. We mostly keep the acid undissociated, which is why we call them weak acids. Yeah. Okay. Do we have time to... Yeah. We're not going to do the whole math, but I want to look at an assumption. Okay? When we have here, if we have Ka equals the concentration of A minus times the concentration of H3O plus divided by the concentration of HA. All right? Which one of these typically has the subtraction in it? Which term? Well, if we look here, let's look at this question. In this question, we start with we have a really kind of miserable reaction here with phosphoric acid. This question is going to take us a long time, all right? A long time. Because we actually are going to deal with both acids at the same time. But I want to show you something, which is, see this number here? Just we're not going to do the math yet today, but I want to show you something, which is down here, we're going to end up with 3.5 molar, right? That's what we started with of our acid, right? We start with H3PO4, and its concentration is 3.5 molar. Here. Right, we're starting with phosphoric acid at 3.5 moles per liter. And we're going to deal with the fact that we're making H2PO4 -1 and H3O plus, right? And those start at 0 for all intents and purposes. What are these? These are getting made, so they go up by X, right? And this is getting used up, so it goes down by x. Does that make sense? Okay, which means this will be 3.5 minus x, right? This would be a good practice question for you, all right? And that means this will just be x, and that will just be x. This would be a good question for you, but I want to focus on this because we can make an assumption. Remember we said sometimes we can make assumptions and they save us work? How many sig figs are we working with here? All right, we're in 2 sig figs. So how big would x have to be to matter? In other words, if this was 3, don't write this. If this was 3.5 minus 0.03, is that going to change our number? No, because that's way over in 2 digits over that don't exist. Does that make sense? What if it was even 0.03? Is that going to change our number? The smallest thing that could make a difference would be this, right? Actually, because it's a 5, this would make a difference. Does that make sense? So in this case, if x ends up being less than 0.05, then it doesn't matter. Then 3.5 minus x is just 3.5. Does that make sense? If x is small enough, it doesn't matter. Can we predict how big x will be? Well, what x really depends on is how big our Ka value is, right? Does that make sense? In the end, when we solve for Ka, when we solve for x, it's based on it being a bunch of stuff equal to Ka. Does that make sense? And we said if Ka is big, then the change ends up being big, right? A big Ka means that we get a lot of products, which means x is big. We make a lot of products. And a small Ka means that we don't make a lot of products, right? So we can actually make a prediction. So here's the rough estimate. For 2 sig figs, if we take the concentration of our acid and divide it by our Ka, if that's bigger than 500, in other words, if we have a lot of acid and we're not going to use a lot of it, then we can say that 3.5 minus, we can say the concentration of HA minus X will just equal the concentration of HA. In other words, we can assume that even though we are going to make some H3O plus and some H2PO4, we're going to do it with just a tiny little bit of our acid, and most of our acid will stay. And so we can save ourselves some math. Because if you look at this question, if this question hadn't had this minus X, would it have been easier math? Way easier, right? We'd multiply that up there, we'd take the square root, we'd have had the answer, right? Does that make sense? So the fact is, the only reason this math was hard was because we had this minus X term. Now here, did the X end up meaningfully changing this? Yeah, it did actually, right? Just a little bit, but we couldn't just use 0.025. But if you look here, that's because our concentration was only 0.025 and our Ka value was 1.8 times 10 to the negative 4. Can you do that division real quick? Tell me what you get. 0.025 divided by 1.8 times 10 to the negative 4. It's going to be roughly 1.2 times 10 to the, and what are we going to get? Negative 4, 3, negative 2, negative 1, times 10 to 2. It's going to be 12. It's going to be around 12, right? Did we get around 12? Give or take? Hello, somebody do that math for me. 0.025 divided by 1.8 times 10 to the negative 4. Anyone? Okay, then you used your calculator wrong. Because you got to make sure you use that scientific notation button, right? Let's try this. Because when we divide by a small decimal, numbers get bigger, right? So that doesn't make sense. 0.025 divided by 1.8 times 10 to the negative 4 should give us, oh, I was wrong, not 100, not 12, 120. So about 138, which is less than 500, right? But it's close. So in other words, this tells us that this number almost won't change at 2 sig figs, right? But doesn't quite clear there. And is that what we saw? It changed, but just a little bit, right? If this had been twice as big, we would have gotten away with it really not changing very much. So the rule is, for 2 sig figs, if you take the concentration of HA and divide it by Ka and get bigger than 500, you can ignore the minus X term. Does that make sense? And that is a simple trick that will make your math a little easier. Now, You don't have to. You can still do the full quadratic and it will solve out and you'll be good. But this can save you a lot of time when you're doing math by hand. If you're using calculator to solve the math, who cares, right? Don't worry about it. But do you see how a little assumption like that can save us time? Now, in math class, will they ever let you just take an x right out of the equation because we think it doesn't matter? No. But we're physics. This is really physics. I mean, it's chemistry, but it's really chemistry right at the border of physics. And in physics, do you know what you are? You're a sphere that weighs exactly 100 kilograms and gravity has a force of -10. And like in physics, we round everything to the nearest whole number and just go and hope for the best. We don't care about wind resistance and right. So if you can make a number go away and it's not going to meaningfully change your answer, you know what pi is for engineers? 3. Absolutely. Who cares? Right? Who cares? They don't care because they're going to over-engineer everything anyway. So sometimes if you want to make sure you're over-engineering, sometimes you make pi 3. And if you're going to be dividing by pi, you make it 4. And you just go, right? You just make sure you're good. They don't care. It doesn't matter. You want the answer that works. So here, this is just a little trick. By the way, if we needed 3 sig figs, what would it have to be bigger than? Not 500, 5,000. If we needed 4 sig figs, it'd have to be bigger than 50,000. Does that make sense? But this little trick here can save you some math. So try this question for homework. See how it goes. I'm also going to print more of these. I'll give them to you tomorrow, but if you want to come get some today, they're just equilibrium practice, but every question has the answer on it, which is nice. So you can check your work. Does that make sense? Yeah. Why is that 500? The math works that Ka is going to tell us how much Ha goes down by, right? So if Ka is really big, then we have to include this x term because it might be 3.5 minus 1.2. And that means...
Excuse the interruption, folks. On today's cafeteria menu, we have a roasted beef vegetable soup for $2, assorted sandwiches for $3 each, freshly made, fully loaded subs for $5, macaroni salad for $3, and today's featured entree is Reuben sandwiches with fries for just $5. Thanks for listening.
You're welcome.
Have a great day, Eagles.
So, but if this number is 3.5 and x ends up being 0.008, then 3.5 minus 0.008 is just going to be 3.5. The fact that we subtracted by x didn't change it, which means when we go to do our quadratic, we could have actually just taken the x out of here and it would have been okay because minus x ends up being the same thing. So does that make sense? If x isn't big enough to change your number, then even though we haven't solved for x yet, it's not big enough to change our number. It doesn't matter. And you can actually try it. You can try this as a quadratic with the x term there, and you can try it just simply without that x term. And here, they're close enough that it's going to make a difference in the second significant digit, and that's not good enough. So here we had to keep the x term. Does that make sense? But sometimes when you do that division, you'll see that HA is 3.5 and KA is really small, 7 times 10 to the negative 3. Do that division. Do 3.5 divided by 7 times 10 to the negative 3. See what you get. Divide it. Yeah, we're taking the ratio. And this is going to be dividing by almost 1 times 10 to the negative 2. So we're going to add 2 zeros onto this. What do we get? Exactly 500, which means we just get away with it here. We just get away with it, but we'll let ourselves get away with it. That means what you're going to see is that if you just treat this number as 3.5, you're going to be okay. It's going to round when we're done, however much this changes by, this might end up being 3.458. But when we round it back, it's still going to be 3.5, which means that for 2 sig fig calculations, we don't need that minus x term. And that makes our math easier. Does that make sense? Try it both ways. So try this. And if you're feeling really brave, try part 2. All right, we'll take it up tomorrow. We're going to keep going on this. How did that feel, generally speaking? Not too bad? Very bad? Terrible? Worst thing ever? It's rough?
Yeah, I'm gonna go home and look at it myself.
Yeah, take your time with it. This stuff's tricky, all right? Stuff is tricky. Put the time in. Yeah. And guys, if you do need help with this stuff, don't be shy. I'm here. If you find me confusing, Chuck's here. If you find Chuck confusing, Khan Academy's here. If you find me, Chuck and Khan Academy confusing, textbooks are here. If you find me, Chuck, Khan Academy, and textbooks confusing, who else here does chemistry? It might be at YouTube. I don't know if we have another chemistry teacher here. Calford could do it. Yeah, Calford could do it for sure. He took chem. He took physical and organic chemistry.